Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week, and going to be talking about satellites and the different types of products that we can get from satellites that can tell us different things about the atmosphere, and there are even applications that go beyond meteorology. It all has to do with what we call electromagnetic energy, which is whizzing through the air at various different wavelengths. The visible part of what we call the electromagnetic spectrum is from zero point 0.4 to zero point 0.7 microns. A micron is a micrometer, or 10 to the minus 6 meters, okay? So if you have 1 meter, then you move the decimal point to the left 6 places, and that's the wavelength. Now, that's what the human eye can detect, but there's lots of other wavelengths out there that the human eye can't see, but they're still there. And the satellite can detect those wavelengths, and we can use that to tell us different things about the atmosphere, and certainly today, a lot about Hurricane Milton. Now, these satellites are what we call geostationary satellites. The acronym for the satellites that we look at is GOES, G-O-E-S, which stands for Geostationary Operational Environmental Satellite. And they are at an orbit height of 22,300 miles. Why at that elevation? Because that is the elevation where the satellite can maintain an orbit of the Earth and move at exactly the same speed that the Earth is rotating. So relative to any one given spot on the Earth, it is staying in exactly the same spot, which is great because then we can do time-lapse imagery, and we can take it as frequently as you want, like every minute, and then you can really see how weather systems are changing or developing or decaying with time. The polar orbiting satellites, which are admittedly much closer to the Earth, but with those you have to wait for it to come back around and make another swipe over your area, so you're not getting a continuous look at any one given spot. So the geostationary satellites, even though they're much higher up, 22,300 miles, they can still give us very, very high resolution imagery, and we can look at any one given spot and see how things are changing over that spot. So that's the basic advantage to it being geostationary. All right, so let me put myself down here in the corner, and we're going to talk about just some basics about this electromagnetic energy. So here we have our trusty satellite, and we have a cloud, and then you have incoming radiation from the sun. Now, the part of that radiation that is visible to us comes in like this. It reflects off the top of those clouds, and then the satellite can detect that. So visible imagery is only available during the daytime, okay? Because obviously when it's dark, there is no energy coming in at that wavelength, and so you have to wait till the next morning to start getting visible imagery again. And this is where the infrared part of the spectrum really comes in handy. So here's satellite number 2, same cloud. The top of the cloud, is emitting infrared radiation, and since the satellite can detect the temperature, it can convert what it measures in terms of how much radiation it's getting off the top of the cloud. It can convert that to a temperature, and then we know that if the cloud is really, really cold, it's got to extend very high up into the atmosphere, okay? So if there's no clouds present, then you're picking up radiation that's being emitted by the Earth's surface, and that's going to be obviously much warmer because it's not at the elevation of these clouds. And so the satellite can also detect that. And this is something that's used in Florida when there's the threat of a freeze and they're worried about the orange crop. If it's clear, then the satellite can detect the temperature of the ground, and it can pick up these little pockets that are going below freezing, and then they can advise the growers in those particular areas to take the appropriate action to protect their crop. And so this can come in really, really handy. And you think about it, the orange growers down in Florida, this is critical to them because they make a lot of money off selling oranges, and if their crop gets wiped out in one night, that makes a big difference for them in terms of income. So another application of these satellites. Now, I'm going to concentrate on 3 different wavelengths. This is the visible part of the spectrum, and again, the wavelength there is about 0.64 microns on this particular imagery. And so you can see Hurricane Milton, and you can see the well-defined eye here. Pretty symmetrical. The clouds extend, the dense clouds extend a little farther off to the west than they do to the east, but overall, a very, very healthy looking system, to say the least. Now, we move on to the infrared part of the spectrum, which is 11.2 microns. The human eye can't see that, but the satellite can detect it. And so what you're looking at here is all these black colors here indicate cloud top temperatures that are colder than 100 degrees below 0 Fahrenheit. Okay, so they extend really, really high up into the atmosphere. And then in the eye, you basically you either don't have clouds at all, or if you do, they're much, much closer to the ground. They don't extend nearly as high as the clouds in the eye wall. And so they show up, excuse me, as a much, much warmer temperature. And so when you see an eye like this in the infrared imagery, that's telling you that this is a very, very well-developed hurricane. And usually the smaller the eye, the stronger the winds are, because if you think about the conservation of angular momentum, in the equation for that, it's a product of the radius times the velocity. So if the radius of the eye gets smaller, in order to conserve angular momentum, the velocity has to get higher. And so with a pinhole eye like this, you can get some incredibly strong winds. And the last advisory had the maximum sustained winds at 180 miles per hour, which is by far and away a Cat 5. So in the middle, between the visible and the infrared, you have what we call a wavelength at 6.9 microns, where the satellite can detect water vapor even if there are no clouds present. So these green colors here are definitely clouds, but the blue colors all the way around the hurricane are also indicative of very, very moist air. The dry air is up here in the yellows and the oranges, and sometimes you'll see this dry air get entrained into the circulation of a hurricane and weaken it, but there's no evidence of that happening right now. This hurricane is embedded in a very moist environment, and there's no indication of either this dry air or this dry air up here getting entrained into the circulation, at least not yet, okay? So this is a product off of an application called RadarScope, where you can actually move your cursor around and do what's called a pixel query, where it'll tell you the value of whatever the satellite is looking at that particular location. So here you see in the eye it has a temperature of minus 22 Fahrenheit. Now that means that the eye is probably not completely clear, that there are a few clouds that aren't nearly as high as the clouds in the eye wall, but they're still there, and so they're showing up at a temperature of minus 22. But let's move out a little bit from the eye and look at this. Instead of being minus 22, now we're at minus 117.7, so almost a 100 degree Fahrenheit temperature difference between what the satellite is detecting in the eye and what it's detecting in the eye wall around the eye. And again, if you have temperatures that cold, it's telling you that those clouds extend very, very high up into the atmosphere, and it is a very, very well-developed hurricane and well-developed eye wall around that very, very small eye. So these are just examples of how different types, different wavelengths of satellite imagery can give us different information about not only the atmosphere, but about the ground. There's even one wavelength where it can detect different types of vegetation, believe it or not. And there are applications there that go way beyond the science of meteorology. So it's really quite a fascinating field, and one that has come a long way since satellites first went up. I think the first weather satellites were back in the 60s. So obviously we're, 50 years, no, 60 years beyond that now. And so a lot has changed, and our capabilities have increased remarkably. All right, that's it for now. That's bonus weather video number 1 for this week. The next one will be coming up on Wednesday. The next daily weather update coming up tomorrow. I will be traveling to New York City tomorrow morning. You can probably guess why. Taking in Game 3 of the Mets-Phillies National League Division Series. And I will be able to get something to you. If there was ever a time where I could take off in terms of local weather, this is it. Okay, there's nothing going on, nor will there be for a week, other than some clouds that are blowing off the top of the hurricane. But in terms of the hurricane itself, I know a lot of you have a great interest in this thing, and how much is it going to strengthen over the next day, day and a half, and then how much is it going to weaken before it makes landfall sometime late Wednesday night or early Thursday morning. And so I will definitely get you an update in some form about all of that during the day tomorrow. Okay, that's it for now. You have a great Wednesday evening, or Wednesday, what am I talking about? Monday evening, what's left of it. And we will talk to you again tomorrow at some point in some form. All right, you all take care, folks. We'll talk to you soon. See you later.